Hello! I'm Anna Lyushchenko.
And I'm Alexander Lyushchenko.
I'm GDE in Flutter and Dart.
I'm GDE in Flutter and Dart too, and I work as a senior staff mobile engineer at Tide.
I work as a senior staff mobile engineer at Tide too. I have 10 years of experience in software development.
And I developed software for more than 13 years.
Okay, then you start the presentation.
Okay, so let's talk about Lego. Lego is a valuable invention. It helps children to unleash their creativity and teaches that by following some algorithm and combining small pieces, you may build complex, beautiful things. What started as a simple toy has overgrown its original idea and become much more than just bricks. Today, you may literally build towns with it. Lego bricks were patented in 1939 and got very few changes from that time. There are so many Lego sets, but what is fascinating is the fact that bricks made in 1958 will work with any modern set as they are of the same size. As a developer, I am impressed by both extreme Lego modularity and maintainability. I mean, isn't it fascinating that you may combine bricks from constructors that your grandfather played with? The idea of combining pieces from totally different sets, like this photo, might sound not that exciting because we are used to it, but in fact it's quite impressive. How can we achieve the same results in software development? As for maintainability, I cannot think of any modern technology as old as Lego that would still be in active use. With Flutter only a few years old, we already see packages that are not working with the latest Flutter. And to develop Flutter apps, we need third-party packages, which we cannot control. What we can control, though, is our codebase. We may make our application modular. By the way, modular programming was developed in the late 60s as a larger analog scale of the concept of structured programming. It's not as old as Lego, but still a mature concept. Already back in those days, developers tried to fight the complexity. Modularity is one of the key concepts that allows us to create reusable code, like reusable Lego bricks, combine it, like Lego bricks, while keeping each piece of the app simple, like Lego bricks. We all know how to create modules. Speaking of Dart, you may think of them as packages. Of course, it's possible to create modules without packages or a package with multiple modules, but let's keep things simple. For this presentation, a module is a package. Packages we create may serve different purposes and thus have different implementations. A package that works with a database has little in common with the package that implements a carousel widget. When developing a project in a modular style, it is important to have an answer to the following question: how to create such an interface that will allow you to combine different bricks? Actually, there are two questions hidden here: how to decompose the app into different bricks or modules, and how to compose them back together. Today, we are going to share our answers to these questions. For this demo, I've created a simple application. You may get the source code by following this QR code. When you just open the application, you will see the list of Lego worlds. That's the first feature. When you tap on a Lego world name, a new screen is opened with characters from that selected world. That's another feature. You may also read details about the selected character by tapping on one from the list.
Let's start with the decomposition. Decomposition is the key to modularity. By splitting the functionality into different modules, we are creating a basement for the whole future project. The decomposition question becomes even more critical if the project is developed by a big team with different sub-teams responsible for different parts of the app. Typically, we divide packages into 3 different types: application, feature, and core. Core packages may include some kind of utilities, common implementations, wrappers over third-party dependencies, etc. They also include a shared domain in case a project has one. Feature packages obviously contain isolated features implementations. Feature packages do not depend on each other to avoid the complexity of the dependency graph, and are only allowed to depend on core packages. The application packages either contain the Flutter application itself, or connect features with each other and provide missing implementations of the abstractions declared in feature packages. There are typically only a few application packages, and they are allowed to depend on both core and feature packages. This separation is reflected in the project's folder structure. While it's more or less clear what's going on inside the core and application, let's look inside the feature folder, which contains our app building blocks. In the demo application, there are 2 feature packages: Lego Worlds, which contains everything that is required for displaying the list of Lego worlds, and the Harry Potter feature, that contains all the code related to Harry Potter universe. Notice how easy and intuitive it would be for developers to find the code. If one of the Lego worlds is missing, the problem is in the Lego Worlds package. If a developer accidentally called you-know-who by name, you fix it in the Harry Potter feature package. Each feature package may contain some or all of these pieces: domain, dependency injection, configuration, localization, presentation layer, navigation, and tests. It looks like there is a lot, but they all have purpose. And when some part doesn't make sense for a given feature, it's safe to skip it. Let's now review each of these pieces of the feature package.
We will start with the domain. By the way, this example does not intend to follow the clean architecture, so do not throw tomatoes when you see that some entities are in the wrong place. The domain layer contains domain models and services that work with these models. Domain models are usually simple and UI-agnostic Dart classes. It is still safe to use any third party here. For example, you can use equatable to simplify writing models, or my personal preference, freezed to get unions, immutable types, and JSON serialization and deserialization. I find it beneficial to have darts or FP Dart here, as this simplifies domain modeling. And of course, retrofit for the networking, maybe even database entities. You may put use cases, view models, services, and entities in the domain layer. Android developers might argue that we messed domain and data layers. Clean architecture fans will support them and claim our architecture not clean. But that's what worked for us the best in the mobile development. And believe us, we tried many different combinations. We do recommend keeping domain entities feature private. When we say feature private, we mean that the code in the feature package is located under the src source folder, and the barrel file does not export mentioned classes. If you think that you need the same model in other features, most probably you need to think twice about feature composition.
Dependency injection is an extremely important part of the overall architecture. It is the glue that connects all pieces together. There are 2 parts to it. The first one is how to glue entities inside a feature. For example, how to instantiate state management classes in widgets, how they will get use cases and repositories as constructor parameters. Here I speak about classes that are implemented inside the feature package. And second is how to provide dependencies from the outside of feature. A feature may declare some abstractions based on which it will behave differently, and expects someone to provide implementations later. Such dependencies are external to the feature, so it is an application-wide dependency injection mechanism. We love code generation, hence we are using injectable in tandem with getIt for both application-wide and feature-scoped DI. At the same time, it is possible to combine different solutions and use, let's say, Riverport in one feature and getIt application-wide. Here is a code that demonstrates how the initialization is done in the example app. We used getIt in both cases, but for the first feature, we registered dependencies with injectable, and for the second screenshot, we do it manually. For the application-wide dependency injection, the same mechanism can be used as for the features. Here, we also register an implementation of the abstract class in getIt manually. Our recommendation is to keep most of the dependencies feature private. All the use cases, repositories, API, blog, or other state management instances should not be exposed from the package and should get into the selected dependency injection mechanism when the feature starts. Only few classes that are declared as abstract in the feature package should be exported in the package barrel file, so their implementation can be provided later with an application-wide dependency injection mechanism. Though it's possible to use different implementations in different packages, still tends to be consistent across features. By configuration, we mean the ability to control the way feature looks or behaves. The decision on specific feature behavior can be made based on multiple sources, such as local or remote feature flags or application flavors. While the feature could potentially access feature flags values provided by the core package, the knowledge of application flavors only exists on the application level. And according to our dependencies direction, feature packages cannot depend on application packages. Thus, we follow this rule. If feature has some configuration points, it declares an abstract configurator class. The implementation comes from the application level, where it can check flavors or other multiple configuration sources to make a decision on whether a feature should provide access to some of its parts, have this or that UI, etc. This is an example from the Lego list feature. It can present the content as a list or as a grid. Thus, the Lego list feature package declares an abstract Lego list configuration class with grid representation boolean. And the application package provides such a configurator implementation to the Lego list feature through an application-wide dependency injection mechanism. Be mindful about the configuration points the feature exposes. Declare as many as you need, but not more. Don't create configuration points in advance because you believe you will need them. Their maintenance is costly.
We recommend always implementing the localization mechanism, even if you are 100% sure that it is not needed. Now, the reason for that is that even if your app will never reach a global audience, you will have a good separation between texts and UI logic. There are two kinds of texts. Common texts have general use words and phrases like OK, back, try again, Wingardium Leviosa, and so on. These words and phrases rarely change meaning out of context, and that makes them common. The majority of texts we recommend putting into features, though. It makes sense to put some common words into features too. Let's take the word back. It can be extremely context-dependent. Instead of a button, it may mean the rear surface of the human body. So for some applications, it might cause confusion after translators localize the app. The localization mechanism is abstracted quite well in Flutter. You may use any solution you like, for example, keeping strings in JSON or YAML files, and any package you like. The tricky part here might be in injecting proper localization delegate, but we will talk about this in a couple of minutes. We recommend keeping localization text feature private, and don't put texts that can have different meanings into common code, even if they look the same. While you may experiment with localization mechanism implementation, we recommend you find one that works for you better and stick with it. It is extremely easy to develop a beautiful UI with Flutter, but it can be easily become messy when different teams are working on different parts of the app. For this presentation, we will not share any special tips and tricks for the UI layer. Here you may find the same code you are writing on a daily basis as Flutter Dev. Same pages, widgets, and state management. The state management is still a hot topic in the community, so let's talk about a bit. For trivial cases, a good old setState will do for the state management. Though probably you would need to introduce a more mature solution very quickly. We recommend you think of state management as a better way of managing widget state. It is still a part of the widget's logic. It doesn't really matter whether you are using Block, Redux, or your favorite state management library. It's just a detail of how widgets interact with other entities and update the visual representation. Modular architecture encourages experiments, so you may use different state management packages inside different features. There is one more extremely important part of the modular architecture implementation. It is the design system. In short, the design system is essential. As a rule of thumb, you should never set any color or font value in a feature. If you have a custom component, like a button for example, consider moving it to the design system so that it will be shared with other features. Every component you extract to the design system must be 100% UI. In other words, it cannot have any logic at all. If some logic is needed, though, create a utility package for it. The design system is essential if you want your app to look consistent. You should not define custom colors or custom atomic widgets in your feature packages. All feature packages must be aware of the design system. The feature's UI itself must be feature private. No other feature should know or make any assumptions regarding the feature look. Feel free to use any state management in your feature. Just pick the one that makes sense. At the same time, don't go completely nuts. Remember that you will have to maintain all of them.
Obviously, it doesn't matter how beautiful and helpful the UI is if it's impossible to reach it within the app. That's where navigation plays a key role. We split navigation into two, internal and external. While they share the same purpose, they are quite different. When we say internal navigation, we mean a mechanism of navigating between pages in a single feature package. It's fully encapsulated inside the feature package and is invisible to the rest of the application. Nobody knows how many screens are inside a certain feature and what logic controls the switching. External navigation is a mechanism for navigating between features. Feature packages cannot depend on each other, and thus features simply don't know other features exist. Feature packages only expose abstract navigator classes with methods to open the other flow, without explicitly specifying the type of the target feature or depending on the specific routing implementation. And it's in the external navigation mechanism where those classes are implemented. By combining these two navigation mechanisms, we are getting full control over the app's navigation while following the modular programming principles. For the code outside of the feature package, the internal navigation is a black box. You are free to use any navigation package for implementing it. However, beware that most of the navigation frameworks offer imperative API, and we prefer to make the inner feature navigation declarative. Thus here, inside the feature, we are using the flow builder from Felix Angelov. External navigation is simpler, as you most probably have already implemented it in several times in your apps. We prefer to use the imperative approach here, which means many navigation frameworks can fit. For the app sample, we've implemented external navigation via GoRouter package. Here is the router declaration that links paths to particular features entry points. It defines localist as the first thing that the user sees when opening the app, and also makes Harry Potter flow respond to /universe/HP path. Outroute library will also be a good choice for external navigation. To navigate from one feature to another, it declares an interface inside the feature package. The Lego list feature does not depend either on the universe package nor on the application package, which contains the router. It only declares an abstract Lego list navigation class with OpenUniverse method, which it calls when the user taps on the list item. It is on the application level where we know about all features of the app. Thus, we provide Lego list navigation implementation from application package through application-wide dependency injection mechanism. That makes features both independent and reusable. I'd like to pay special attention to a feature entry point, which is targeted by external navigation. Obviously, it cannot be a specific page, as all pages are feature private. There must be another widget to navigate to. We call such widget flow. The flow serves as an entry point to a feature. It is responsible for instantiating feature dependencies, providing correct localization delegate down the widget tree, and wrapping the internal navigation, that in this particular example is represented as a flow builder. This usually tiny class is the main class of Lego-style programming. It represents the input interface for the feature and allows the encapsulation of feature internals. Here is an example of the flow implementation. It calls the initialize function that pushes a new scope with dependencies, provides the localization delegate, and calls the flow builder constructor. That wraps up the navigation topic. To recap, we recommend splitting application navigation into two, internal and external. Internal navigation is recommended to be declarative. It's just simpler and looks more organic when you map the flow state to the navigation stack. The external navigation is simpler when it is imperative. External navigation cannot open a page from a feature package because pages are feature private. It always opens flows, special classes that initialize features and behave as entry points for internal navigation. While it's possible to implement everything with external navigation only, we highly don't recommend that, as you will need to expose feature internals, which will break the feature's encapsulation.
Last but not least, tests. In this presentation, we've been talking about many different entities. Of course, we need to prove that they behave as intended. The best way to do this is to write tests. Here is how we typically write tests. Each file in the source code has a dedicated test file. Each entity in this file has a dedicated group of tests in the test file. This approach is called solitary testing, and there is nothing wrong with it. At the same time, this is not the only way to prove that the feature works. Remember, we have an entry point for the feature, a flow class. What if we mostly focus on this class? We may say that other classes are implementation details for the flow. That would be a sociable testing approach. We allow the feature to use real block, real localization, real DI, and real domain entities. We are using Gherkin for testing our features. We write tests in a natural language. These tests behave as documentation for the feature and validate that the feature works. From our experience, it is possible to cover 95% of the feature with these feature tests. Moreover, these tests can be shared with integration tests, so by writing feature tests, you are doing integration tests too. Of course, not everything is possible to cover with Gherkin. For entities from core packages, we recommend using plain old unit tests. Consider thinking of your feature as a black box, even from tests. The code coverage will show you what is needed in the feature and what possibly can be removed as non-essential. Test real feature internals and limit mock usage. Write reusable tests. We don't recommend starting with one-to-one mapping in the first place. Be brave and give sociable testing a chance. We've reviewed all entities from the feature packages. Due to time limits, we will not go to the IDE, but the sample app is already on GitHub, so I hope you will check it after the presentation. That is what you will see there. In the root folder of the repository, there are 3 folders: app, core, and feature. They contain appropriate pieces of the app. The Lego app folder contains an extremely small package. It has the material app only. The rest is in other packages. The Lego configuration contains implementations for the configuration classes of the features. The Lego navigation contains external navigation. The core folder has the design system package only. In this example, the design system is just a theme, but in the real world, it's a beautiful package with tons of custom widgets and no business logic. The most exciting part is the feature packages. As you may see, there are different. The mandatory parts are the flow folder with the feature entry point and the barrel file that exposes the entry point. The rest depends on the feature. Feel free to explore these folders. Do not hesitate to catch Anna during the conference or reach me on Twitter if you are interested in details.
The real-world application written in Lego style may consist of hundreds of packages. We prepared some advice on how to rule them all and stay sane. You already noticed that a typical feature could consist of many entities. You don't need to create them manually. After implementing the first couple of features, you will see what is needed and what is entirely optional for your app. We recommend you spend a day creating a custom Mason template that will generate feature packages for you. It would be beneficial to create templates for parts of the features too. Visual Studio Code users may install the Mason plugin. It allows to generate code straight from the IDE. After creating many feature packages, you might want to run some commands in them. For this, you may use malloc. It is essential on the CI, as you may run analyzer or tests only on changed packages. So in the end, that dramatically speeds up the development. As for your working environment, try to focus on a single feature at a time. It's much easier to separate features when you think in the context of a single feature only and treat all other features as third-party dependencies. If you see that you still switch the context all the time, consider opening a single feature package in your IDE instead of the whole project. If you use code generation, leverage a build YAML file and set up build runner in such a way that specific builders will look into specific folders only. That will significantly speed up the code generation and force everyone on the team to use the same feature package structure.
Why you may want to try this approach? It is perfect for A/B testing and experiments with code. You may implement the same feature but with slightly different behavior or use different frameworks and find what works best for you and the app users. By keeping features separated, you improve the maintainability and reusability of the code. You may create truly beautiful applications from small atomic isolated features for as long as the contract you choose is in place. You may review the code by scanning this QR code. Thank you. Now we are ready to answer your questions.